Math 2414, trigonometric integrals, integrating a product of secants and or tangents, part 2. In the previous video, which was our first example of integrating tangents and secants, we tried two different substitutions, u equals tangent x and u equals secant x. One succeeded, one failed, and we kind of described under what conditions one should fail, and under what conditions each substitution should succeed. And I've summarized those here. If you're integrating a product of tangents and secants, I've called the power on tangent P and the power on secant Q. Then here are the two strategies we kind of summarized in the previous video. If Q is even, in other words, if you have an even number of secants, use u equal tangent. You're going to borrow a secant squared for the du. That will leave the secants even. Then you can use secant squared equals 1 plus tangent squared to rewrite the unwanted secants. But if the power on the tangent is odd, and it wasn't last time, which is why this substitution failed, but if the power on the tangent is odd, your substitution is u equals secant of x. Then you would borrow secant tangent for the du. That would lower the tangent from an odd power to an even power. Then you can use tangent squared equals secant squared minus 1 to rewrite the unwanted tangents. Now this is a lot to try to just commit to memory. So my recommendation is this. When you're integrating secants and tangents, you pretty much have one of two big choices. Try u equals tangent, try u equals secant. Just try one. But when it comes time to get rid of your unwanted trig functions, it better have an even power. That way you can use a Pythagorean identity to get rid of them. So if you're worried about remembering this, just remember, try tangent, try secant, but the consistent thing, and this goes back to sines and cosines, the consistent thing on all of these is whatever substitution you use, when it comes time to pull the substitution off, your unwanted trig functions, in other words, the ones that aren't your substitution, should have an even power so that you can use a Pythagorean identity to change it to your wanted trig functions. So if Q is even, you do one thing. If P is odd, you do another, which begs the question, what if P is odd and Q is even, like this one? And the answer is you really can't go wrong. Just choose something to run with it. So yes, we are going to do this one two different ways. We're going to use this strategy when the secant power is even by saying u equals tangent x, and we'll use this strategy where the tangent power is odd and say u equals secant of x. But again, you can memorize words and steps all day long, but if you understand what you're trying to make happen, just jump in. If it works, great. If it doesn't, go back, try the other one. Let's try letting u equal tangent x. Which, by the way, should work. This is the substitution we pull when the power on the secant is even, which it is. But let's just pretend we didn't say all that. Then du is equal to secant squared of x dx, which means that we want to pull off a secant squared for the du package. So we'll leave the tangents alone for a minute. Pull off two of the secants. Leave the other two behind for the du. Take inventory. That du needs a secant squared and a dx, which it has. All this becomes du. The trig function I want is tangent. Here's three of them. This becomes u cubed. The trig function I don't want, the unwanted trig function is secant squared. That has an even power. That's good. I can replace secant squared with 1 plus tangent squared. Tangent is my wanted trig function. In case you missed it, yes, I dropped and caught the cap in one move. I'm a little ninja like that, but don't tell anyone. But anyway, as I was saying, we didn't want the secants. We had a secant squared, which we could replace with 1 plus tangent squared. We do want tangents. That becomes u. This becomes 1 plus u squared. And at this point, the integral is really straightforward. We need to integrate this product, but we don't integrate products, so distribute to make u cubed plus u to the 5th du. So we can insta-integrate and unsubstitute in one move. I do like my powers highest to lowest, so we'll start here. This would be 1/6 u to the 6th, but u is tangent. So 1/6 tangent to the 6th x, plus this will be 1/4 u to the 4th, but u is tangent. So 1/4 tangent to the 4th x plus c. So this is what happens if we said u is equal to tangent of x. And it worked, and there's no need to do the problem again. And you may be wondering on a homework question or a test question, what if I choose one and you're expecting the other? Well, if they both work, I'll accept either. But let's see what would have happened had we chosen instead to let u equal secant x. Because again, if you're worried about remembering all this, I totally understand. Prior to making this video, I had to think about how all this worked and write it down. But I understand the premise behind it. So if you understand the premise behind it, you don't have to memorize any of this. Just try something and know what to look for. If you see it, great. If you don't, stop and do the other one. Let u equal secant x. If we try this one, then du would be secant x, tangent x, dx. So let's peel off everything we need to make our du package. We need a secant and a tangent. So each one's going to give up a trig function. Tangent cubed is going to get dropped down to tangent squared. Secant to the fourth is going to get dropped down to secant cubed. Because we borrowed one of each, we borrowed a secant and we borrowed a tangent to put with the dx to make the du package. The secant, the tangent, the dx. All this becomes du. Our wanted trig function was secant. And we have three of them here, so this is a u cubed. Our unwanted trig function is tangent, but its power is even, so we're on the right path. We can replace tangent with secant squared x minus 1. I wasn't kidding when I said you need to know those identities. Secant is the wanted trig function, so this becomes u squared minus 1. Now this is easy to integrate. Let's go ahead and distribute the u cubed to get u to the fifth minus u to the third. Because we don't integrate products, we integrate sums and differences. Let's integrate and unsubstitute. 1/6 u to the sixth, but u is secant. So 1/6 secant to the sixth x minus 1/4 u to the fourth, but u is secant. So 1/4 secant to the fourth x plus c. And this is if u is equal to secant of x. And you may be thinking, but these answers look totally different. And you're right, but I bet you could show they're equal. How? How would you show this is equal to that? Well, classic problem-solving strategy. Change what you don't want. I know that secant squared is 1 plus tangent squared. So I can write this as secant squared squared, change it to 1 plus tangent squared, get ready to bust that open. This is secant to the sixth, so I can write that as secant squared cubed. So I could write this as 1 plus tangent squared cubed, along with the minus 1/4 and the 1/6. If we multiplied it all out, distributed, gathered like terms, maybe pulled off a little bit more identity shenanigans in the middle. I haven't played it out, so I'm not sure what all would happen there, but it should boil down to here. Now, it may be off by a constant, but that's okay because a constant plus a constant is just a different constant. All right, so to summarize what you've seen so far in part 2, to integrate a product of secants and or tangents, it all depends upon whether or not secant has an odd power, that u equal tangent, or tangent has an, let me try that again. It all depends upon whether secant has an even power, let u equal tangent, or tangent has an odd power, let u equal secant. But regardless of your choice, and I can't stress this enough, do something. And the time you'll know when it works is when you get to the unwanted trig functions after making your du. If the unwanted trig functions, the one that don't match your substitution, have an even power, a Pythagorean identity will fix that. That's how you know you're on the right track. All right, the next video, I just want to show you 2 specific examples of secants and tangents.